All right, get ready, because we're diving deep into galaxies today.
Yeah.
We got a paper sent in by Fritz Zwicky from 1933.
Wow.
Talk about a blast from the past. It's all about those mysterious extragalactic nebulae, which we now call galaxies, of course, in this weird thing they do.
Yeah.
Redshift.
Oh, this is a fascinating one. It's like a time capsule, this paper.
Right.
Published in Helvetica Physica Acta,
Right.
a real snapshot of early 20th century astronomy. Back then, galaxies beyond our own. Mind-blowing stuff.
I know, right? Imagine trying to wrap your head around that for a first time, and then Redshift just throws another curveball.
Yeah.
It's like, imagine a car speeding away from you.
Okay.
The sound of its engine, and it seems to drop in pitch, right?
Exactly. Similar thing happens with light. As an object moves away, the light waves stretch out.
Yeah.
They shift towards the red end of the spectrum. It's impressive. Even back then, Zwicky was already laying down the law.
Yeah.
What a solid theory of redshift would need to explain.
He was really committed to the science.
Oh, yeah.
Commanding the evidence, not just jumping to conclusions. So how did he even begin to measure distances to these nebulae? They're so far off, it must have been like mapping uncharted territory.
Well, he had some pretty clever methods for the time, like using these stars called Cepheid variables.
Okay.
They've got this unique property. Their brightness fluctuates
Right.
in a predictable pattern, and that pattern directly linked to their true luminosity.
So it's like a built-in brightness control
Exactly.
that tells you how much light they're actually putting out.
Yeah.
And once you know that, you can compare it to how bright they look to us and figure out the distance.
You got it.
Pretty ingenious.
It was groundbreaking. But what about nebulae so far away that individual stars were too faint? Zwicky had a solution. Statistics.
Ah, so he looked at the overall brightness of the whole nebula.
Exactly. He compared the brightness of the brightest stars in a nebula
Okay.
to the brightest stars in our own galaxy.
Makes sense.
Thinking was, the distribution of star brightness should be similar across different galaxies.
That's a pretty big assumption, though.
It had its limitations. But don't forget, this was early days in exploring galaxies.
Right.
These techniques were laying the groundwork for what we know now.
Okay, so we've got ways to estimate distance. But then there's this whole redshift riddle. Most of these nebulae seem to be rushing away from us.
This is where it gets really interesting. As Zwicky talks about Edwin Hubble's work, he made a remarkable observation.
Let me guess. He found that the farther away a nebula is, the faster it's moving away.
Spot on, and that led to a revolutionary idea. The universe itself is expanding.
Right.
Like the fabric of space-time is stretching, carrying galaxies along with it.
Mind-blowing. But this paper was published before the Big Bang Theory was widely accepted, right?
Exactly. So Zwicky was dealing with a different set of explanations for this expansion.
I see.
Some involved modifications to gravity. Others suggested light might lose energy
Okay.
as it travels those vast cosmic distances, causing the redshift.
Interesting.
It was a time of intense debate and exploration.
Must have been exhilarating to be on the forefront of those discoveries, even if the picture wasn't totally clear.
Absolutely. But like any good mystery, there were some pieces that didn't quite fit. Zwicky points out observations that seem to contradict Hubble's findings.
Oh, what kind of observations?
For example, measurements of apparent motions in nebulae, made by Adrian van Manen. These measurements suggested some nebulae might be rotating,
Really?
which wouldn't fit with the idea of them just moving away.
Yeah, it's like having two puzzle pieces that should fit, but they don't
Right.
fit what was going on.
These discrepancies fueled scientific debate,
I bet.
highlighted the importance of careful interpretation. Were the measurements flawed? Was there something else happening?
Right.
These were the questions that drove further research, led to a more nuanced understanding.
So Zwicky laid out this redshift mystery. Did he have any explanations of his own?
He explored two main categories of explanations.
Okay.
Cosmological theories based on Einstein's relativity, and theories about how light interacts with matter.
Okay, let's break those down. Cosmological theories, those sound intense.
Well, picture the universe like raisin bread dough as it bakes. The dough expands,
Yeah.
and the raisins, they move farther apart.
I'm with you.
The raisins are the galaxies, the dough is space-time itself.
Right, I see it.
That's the basic idea behind an expanding universe.
Right.
From any raisin's viewpoint or galaxy, all the other galaxies look like they're moving away. The farther away, the faster they seem to be going.
And that's where the redshift comes in.
Exactly. It's a consequence of this expansion. But Zwicky also considered other possibilities, like redshift being caused by the curvature of space-time.
So space isn't just expanding, but it might be warped or curved?
You got it. Pretty mind-bending stuff, even for astronomers.
I bet. Okay, so those are the cosmological theories. What about the light and matter interaction ones?
This is where it gets even more interesting. One idea was that light might lose energy as it travels over those vast cosmic distances, causing its wavelength to increase and shift towards red. This energy loss could be from interactions with interstellar dust or gas, or even some unknown particles.
So light gets tired on its journey.
Good way to put it. Zwicky even proposed this gravitational drag, where the gravity of matter in the universe slows light down a tiny bit, causing a redshift.
Wow, so they were figuring out if the universe was expanding and trying to understand light itself.
Exactly. And Zwicky, being the thorough scientist he was, carefully looked at the strengths and weaknesses of each theory.
Yeah.
He pointed out we needed more observations, better models, to really crack the redshift code.
Did he have a favorite theory, or was he leaving it open?
He actually concluded that none of them were entirely satisfactory at that time. He left the door wide open for more research. Shows his scientific integrity.
It sounds like he was setting the stage for a whole new era of cosmology.
He absolutely was. But there's one more twist.
Oh?
Zwicky's paper also looks at the Coma Cluster.
The Coma Cluster. What's so special about that?
It's a massive group of galaxies, and it gives Zwicky a puzzle that would lead to one of the biggest mysteries in modern cosmology. But that's a story for part 2 of our deep dive.
Ooh, a cliffhanger.
Ugh.
Well, I can't wait to hear what Zwicky found in the Coma Cluster.
Yeah.
But for now, I think we've had an amazing journey through early galaxy research. Stick with us. The adventure continues. Welcome back. Still thinking about that journey through early galaxy research. We're looking at this paper by Fritz Zwicky from 1933.
Yeah.
And it's full of insights about redshift, expanding universes,
It is.
and a mystery in the Coma Cluster. I gotta know what he found.
This story really shows Zwicky's brilliance and his willingness to think outside the box. Remember, this was before the Big Bang Theory was widely accepted.
Right, like solving a puzzle with missing pieces.
Exactly.
So how does the Coma Cluster fit in?
Well, it's this huge group of galaxies. And Zwicky was looking at how they moved within the cluster.
Okay.
And he realized something was wrong, something that didn't make sense with the physics they knew back then.
So we got a cosmic mystery.
We do.
What was so strange about what he saw?
He saw the galaxies in the Coma Cluster moving way faster than they should.
Really?
Based on the cluster's visible mass, like some unseen force was holding them together, stopping them from flying apart.
Like a flock of birds swirling in formation, but there's no reason they're staying together.
Perfect analogy. Zwicky realized the gravity from the visible matter, the stars and gas.
Yeah.
It wasn't enough to explain those speeds.
So what did he think it was? Did he have an idea for this invisible force?
He proposed that there must be a lot of unseen matter in the cluster, matter that doesn't emit light but still has gravity. He called it Dunkelmaterie, dark matter.
Dark matter. That's a pretty cool concept.
It is.
So he was saying there's a whole hidden universe, invisible to us, but affecting how galaxies move.
Exactly. And his observations of the Coma Cluster, they were some of the first evidence for this dark matter.
It's amazing he was already thinking about dark matter back in 1933, almost 100 years ago.
It shows how forward-thinking he was,
Yeah.
willing to consider these radical ideas. And you know what's even more interesting?
What's that?
Zwicky also briefly mentions a connection between dark matter and cosmic rays.
Oh yeah, those high-energy particles from space.
Right. He suggests that if dark matter exists, it might interact with those cosmic rays, maybe influencing their energy and direction.
So dark matter could be shaping the universe with its gravity and affecting these tiny particles.
That's the idea. It was just a brief mention in the paper, but it's a thought-provoking idea.
Yeah.
One that still intrigues astronomers today.
It's like dark matter is this multitasker affecting the universe in ways we're still trying to figure out.
It is.
This deep dive is showing me just how much we still don't know about the cosmos.
And that's what makes it so fascinating. Zwicky's work, even from almost a century ago, is still shaping our understanding
Absolutely.
and inspiring new research.
This paper is full of surprises. Anything else we haven't covered?
Actually, there's one more thing about Zwicky's work that we should look at. His exploration of different explanations for redshift explanations that went beyond the expanding universe. It's a glimpse into the scientific thinking of his time.
Okay, I'm ready for another mind-bending trip through cosmology history. Let's do it. Okay, let's dive into those alternative redshift theories. It's amazing to think that the expanding universe wasn't the only idea back then.
Yeah, it's easy to forget how much we've learned since then.
What other explanations were they considering in the 1930s?
Well, remember how Zwicky talked about those two main categories?
The cosmological theories and the ones about light interacting with matter.
Exactly. We explored the cosmological ones, like the expanding universe.
Right, those are pretty wild.
They were.
So what about the other category? The ones focused on light and matter.
One idea was that light might lose energy as it travels those incredible distances across space,
Okay.
causing its wavelength to increase and shift towards the red end of the spectrum.
I remember that.
This energy loss could be due to interactions with stuff like interstellar dust or gas or even some unknown particles out there.
So it's like light gets tired on its journey through the cosmos.
Yeah, that's a good way to put it. Zwicky himself even proposed this idea of gravitational drag.
Gravitational drag.
Yeah, where the gravity of all the matter in the universe could actually slow light down a tiny bit, causing that redshift.
That's a cool idea, but wouldn't we have noticed if light was slowing down? Wouldn't that have messed up our other observations?
You're right, and that's a big part of why those alternative theories were eventually ruled out. As our telescopes and measurements got better, the evidence really pointed to the expanding universe as the best explanation.
That makes sense. It's still fascinating to think about all the different possibilities they were considering back then.
Definitely. It shows how science is always evolving,
Absolutely.
refining our understanding of the universe.
For sure. This whole deep dive has been incredible. We've uncovered so much from this one paper by Zwicky.
It really is a remarkable piece of work.
His methods for measuring galaxy distances, his exploration of redshift, the early hints about dark matter.
And his openness to considering different explanations.
I know. It's amazing how relevant it still is almost a century later.
It speaks to his genius.
Absolutely.
And his lasting impact on astronomy. His work has really shaped how we understand the universe today.
I have to admit, I started reading this paper thinking it would be a fun little history lesson.
I get that.
But it's turned into so much more. It's a reminder that even groundbreaking discoveries often leave us with more questions than answers.
That's the beauty of science, isn't it?
It really is. And those unanswered questions are what drive us to keep searching and exploring.
Exactly. So the next time you look up at the night sky and see all those stars, remember they hold secrets that we're still trying to figure out.
And maybe one day, it'll be one of our listeners who unravels those mysteries and adds their own chapter to the story of scientific discovery.
That would be amazing.
Until then, keep looking up, keep wondering, and keep those cosmic questions coming. Happy stargazing, everyone.